Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be setting up this centrifugal pump case. Now the geometry here is actually quite realistic and is industry standard. So we are just going to be looking at it and splitting it into different meaningful boundaries, and we'll be applying the required boundary conditions and so on. Now here I have a list of boundaries that I've already created, and you can see that currently no triangles are being assigned to it. Make sure that all of these boundaries are filled up. Alright, so couple of things that we need to check first. I'm running the diagnosis and you can see that there are no errors, so that's a good thing. So what I'm going to do is I'm just going to maybe look at the impeller from different angles to basically understand the geometry first. So I'm just going to draw this box around and I'm going to select like one half of triangles and use Control H to basically hide them. And now you can actually see the cut section. So here you can see that the impeller geometry is quite detailed. So that's why I said it's a very realistic centrifugal pump. The diameter of this particular impeller I believe is around 20 centimeters. We can measure that exactly. And you can see that there seems to be a very small gap, between the impeller and the housing or the volute, which is fine. Alright, so how do we systematically go about this? Well, if you basically look at a centrifugal pump, it has the following parts. The intake, so we have the inflow boundary, so this is where the flow is actually coming into the computational domain, and similarly outflow, that is where the flow actually leaves. And then we have the intake runner, which is basically like this entry length. So for example here, this particular cylindrical section that you have that meets the eye of the impeller, that is called as the intake runner. Typically it's a bit longer. Again, in our case, we don't have experimental data. We are just going to, apply reasonable boundary conditions to it. So this length should be sufficient. Ideally, what happens is a sufficient amount of intake length is provided, and at the inlet, measured boundary conditions are given. So typically, total pressure boundary conditions are given, right? So we have the shroud, which is basically this particular area. And then we have the impeller and we have the volute, which is basically the casing. So how do we go ahead and flag this? Well, it should be fairly straightforward. I should be able to use the angle method to get the inlet. There you go. So that looks good. So here what I'm looking for is I'm looking for a region where I can create a boundary flag, and I'm going to be using the arc method to see if I can select an entire circle. So here you can see that a selection is made, but it's sort of irregular. So maybe not that one. So how about this one? So this one looks fairly regular to me. So I'm going to mark this as a fence. And what I'm going to do is I'm going to click on reconstruct fences from existing boundaries to get the top one as well. And then for the intake runner, I'm going to use the boundary fence method and I'm going to select this guy and apply. Alright, awesome. So that looks good. So what I'm going to do next is just hide the inflow and the intake runner so that we get improved visibility. Alright. So you can see that the shroud kind of ends here. So I should be able to go back to fence, use the arc method and select this particular guy. That looks pretty good to me. So let's hit enter to create the boundary fence. And always verify, alright. So whenever you create a boundary fence, you need to look at the geometry completely to see that the edges have been flagged incorrectly. So then let's go to flag, and then we're going to click on the shroud, use the boundary fence method. Boom, there you go. That selection looks good. And let's click apply. Okay, so now I think we can hide this guy. And what I'm going to do is I'm going to quickly add the outflow. This should be easy to select. I should be able to use the angle method and select that guy. Perfect. So that's just great. What else can I do here? Well, the volute can now be selected. Before we do that, we need to first click on reconstruct fence from existing boundaries. So you can see that my thought process here is quite simple. I first flag the easy boundaries and then I use that to create fences and then flag subsequent boundaries. So this approach works very well for turbo machinery applications. So in this particular case we have a fence there. So let's go back to flag. Let's select the volute geometry and we're going to use the boundary fence option and select it. Perfect. So that looks good. Let's hide the volute. So now we're left with like three components, right? So there is the impeller bottom, which is just this particular face. So I should be able to use the angle method and add it. And then right about here, that is basically the impeller sweep. So you have the impeller and the geometry has been swept to create that cylindrical ring, right? So that structure is what I call as impeller sweep. And I'm just going to add it right there. So now whatever is left is basically your impeller. So I can just hide everything and I can just enable this guy, and if you rotate it, you can clearly see that that's just the impeller. So I'm just going to use the boundary method to select all the triangles here, click on my impeller and click apply. So now let me click on show all, and that's it. So the boundary flagging is complete. So let's enable all the normals. Let's go to diagnosis and run it one more time, and that's basically it. So with that, our geometry cleanup and surface flagging is done. In the next video, we'll be going over the boundary conditions for this particular case. I'll see you in the next one. Bye.